Truly consider just how incredibly stable everything around you is. Your coffee cup, the chair you're sitting on, even you yourself were all made of atoms.
Right, fundamental building blocks.
And then inside those atoms, there's mostly empty space, right? But what if I told you that seemingly empty space is actually humming with invisible waves?
Uh-huh.
And those waves are directly responsible for why everything holds together, why it's structured, and why it doesn't just dissolve into chaos.
It's a truly profound realization, isn't it?
Yeah.
That the very fabric of reality at the quantum level is dictated not just by what is there, but by what cancels itself out.
Exactly. So today we're taking a deep dive into a concept we're calling frequency cancellation. Think of it as the universe's ultimate bouncer, allowing only certain quantum notes to play, and in doing so, it underpins the very stability of matter.
It's a really intuitive analogy, actually. Powerful, too. It helps us understand the fundamental structure of atoms and, well, the nature of reality at that quantum level.
Our mission today is to give you a shortcut to understanding one of science's most profound mysteries.
Yeah, we've pulled insights from quantum physics, chemistry, even a bit of engineering to unpack this idea for you.
And what we're going to explore is how this idea of frequency cancellation, which is really a direct parallel to the more formal concept of destructive wave interference,
Right.
how it explains why electrons only exist in specific, allowed states, the intricate and often surprising shapes of electron orbitals, and even that abstract property we call electron spin.
It's a journey right into the mechanics of reality itself.
It certainly is. Where should we start? Maybe with the old classical problem.
Let's do that. So, back with classical physics, the picture was, well, flawed. According to those ideas, an electron orbiting a nucleus should continuously radiate energy, like a tiny antenna.
Okay, radiating energy, so it loses energy.
Exactly. And if it did that, it would quickly spiral inwards faster and faster and just collapse into the nucleus.
Meaning atoms would be incredibly unstable, which they clearly aren't.
Right. Clearly, that's not what we observe. So what prevents this, fundamental catastrophe?
And this is where quantum mechanics comes in and just flips the script.
Completely. It provides the answer by introducing this revolutionary idea that particles, like electrons, also behave as waves. De Broglie's big insight.
And this isn't just some quirky side note, is it? This wave nature is the reason for quantization.
Precisely. It's why properties like energy don't exist on a smooth, continuous spectrum, like a ramp. They only exist in discrete, specific values, like steps on a staircase.
Okay, steps. And the math that describes this, that's the Schrödinger equation.
That's the one. And, for anyone familiar with quantum mechanics, it's more than just a formula. It acts like a sophisticated filter.
A filter? How so?
Well, for an electron that's bound within an atom, this equation only has valid, stable solutions for specific, discrete energy values.
The eigenvalues.
Those are the eigenvalues, yeah. And each one corresponds to a stable wave function, an eigenfunction, which is basically the mathematical blueprint describing that stable wave pattern. It finds which wave patterns can actually exist without falling apart.
So if the Schrödinger equation acts as this filter, what exactly makes a wave pattern unstable so it gets discarded? Is it just messy?
That's a fantastic question, and it gets right to the heart of it. It's where the idea of constructive interference comes in.
Ah, waves adding up.
Exactly. Imagine an electron as a standing wave around the nucleus. Maybe picture a plucked guitar string, but wrapped in a circle.
Okay, I can visualize that.
For this wave to be stable and self-sustaining, it has to interfere constructively with itself. That means wave crests must perfectly meet crests, and troughs must perfectly meet troughs after each revolution around the nucleus.
Ah, so it has to line up perfectly with itself.
Perfectly. And that imposes a strict geometric condition. It means an integer number of wavelengths, 1, 2, 3, etc., must fit exactly into the orbit circumference.
Nye Elit's 2-bar. That old Bohr model condition, but now explained by waves.
Precisely. That integer relationship n is the physical origin of those quantized energy levels in stable orbits.
And this is why the lowest possible orbit, the ground state where n1 is, stable.
Yes. It's simply the smallest space a single wavelength can constructively fit into around the nucleus. It physically prevents the electron from spiraling further in because there's no stable lower energy standing wave pattern it can form.
It literally can't fit a smaller stable wave. So if it can't be just any wave, what happens if it tries to be an in-between state, like say n equals 1.5? Does it just fizzle out?
Exactly. That's where our frequency cancellation idea really shows its power. If an electron tried to exist in some hypothetical NN1 1.5 state, its wave would be completely out of phase with itself after one loop.
Crest meets trough.
Crest meets trough. Total destructive interference. It leads to immediate cancellation and self-annihilation.
Wow. So these invisible phases aren't just unobserved, they're physically impossible to maintain.
Physically impossible. The electron wave can only exist where it's in phase with itself. Any other configuration results in its own self-destruction through interference.
So that's the ultimate reason for the stability of matter.
Fundamentally, yes. The electron is essentially forced to occupy the lowest energy stable standing wave, the ground state, because all those intermediate energy states are literally canceled out by destructive interference.
It's like the universe has built-in rules. Nope, you can't be that wave, you'd just vanish. Stability isn't passive, it's an active consequence of wave mechanics.
Absolutely.
Now that 1D model, the wave in a circle, is great for grasping the basic idea of quantization. But atoms are three-dimensional, right? And electron wave patterns, the orbitals, they're way more intricate than simple circles.
They certainly are.
So how does this concept of frequency cancellation extend to shaping those complex 3D structures we call atomic orbitals?
Right. So when we take the Schrödinger equation and solve it for a realistic 3D atom, the solutions, those stable standing waves, are defined by not just one, but a set of three quantum numbers.
NL and ML. I remember those from chemistry.
Exactly. NL and LL. They emerge naturally from the mathematics and basically act as parameters that define these 3D standing waves, which we call atomic orbitals.
Okay, so the principal quantum number, N, that's the one we were just talking about, it defines the overall energy level and sort of the size of the orbital.
Correct, like the fundamental harmonic of the 3D wave. Higher N means higher energy and generally a larger orbital, further from the nucleus.
Got it. And then L, the angular momentum quantum number, that dictates the shape.
Precisely. L defines the shape of the orbital and the angular complexity of the wave pattern. So if L is 0, you get an S orbital, which is perfectly spherical.
Simple enough.
If L is 1, you get a P orbital, which has that familiar dumbbell shape, 2 lobes.
Right.
And for L equals 2, you have the D orbitals, which often look like clover leaves or have more complex shapes.
And the third one, L, is the magnetic quantum number.
That one defines the orientation of that specific orbital shape in space. So for a P orbital, where L1, ML, can be -1, 0 + 1, telling us if the dumbbell is aligned along the X, Y, or Z axis.
Okay, so these numbers together define the specific 3D wave pattern. And it really drives home that an atomic orbital isn't a fixed path like a planet orbiting the sun.
Not at all.
It's more like a probability cloud.
The distribution.
Exactly. It's a probability distribution. It's described by the wave function, Ci, and the square of that function tells us the probability of finding the electron in any given region of space.
Now, here's the really cool part, I think. How does frequency cancellation show up in these 3D shapes?
Visually, it shows up as nodes. These are surfaces in 3D space where the electron wave function is exactly 0.
0, meaning?
Meaning there's 0 probability of finding the electron right there on that surface.
Wow. So these nodes aren't just empty spots. They are literally the physical evidence of perfect frequency cancellation within the electron's own 3D standing wave. Precisely. It's where opposite phases of the wave think, positive and negative amplitudes, meet and cancel each other out completely.
So like the quiet spots in a noisy room if the sound waves cancel?
That's a great analogy. And there are two main types in orbitals. First, we have radial nodes.
Okay.
These are spherical surfaces at fixed distances from the nucleus. For example, a 2s orbital isn't just one big sphere. It's a sphere containing another, smaller spherical node inside it. This node separates an inner region of probability from an outer region.
So like an onion layer where the electron can't be?
Kind of, yeah. The number of these radial nodes is given by the formula NL1. So a 2s orbital, N22L0, has 2, 0, 1 equals 1 radial node.
Okay, makes sense. Any other type?
The other type are angular nodes. These are usually planar or sometimes conical surfaces that pass right through the nucleus.
Through the center.
Right through the center. That dumbbell shape of a p orbital. That's because it has a single planar angular node slicing right through the middle, separating the two lobes.
So the two lobes are out of phase?
Fundamentally out of phase with each other. If one lobe corresponds to a positive wave amplitude, the other corresponds to a negative amplitude. The plane between them is the surface of perfect cancellation.
And the number of angular nodes is just L.
Simple as that. L0
Yep.
orbital, 0 angular nodes, hence spherical. LOME orbital, 1 angular node, hence the dumbbell. LiPo, d orbital, 2 angular nodes, hence the more complex shapes.
And the total number of nodes, radial plus angular, is always in 1.
Always in 1. It's a beautiful, consistent mathematical structure. It shows us directly that the specific, intricate shapes of atomic orbitals are purely a consequence of where these standing waves are forced to cancel themselves out to remain stable.
This isn't just abstract geometry, then. These cancellation zones, these nodes, they are literally the blueprint for the entire periodic table.
Absolutely. They dictate how electrons arrange themselves, how atoms can bond with each other by overlapping orbitals, how materials behave. Fundamentally, why chemistry works the way it does.
It all comes down to how these waves are allowed to set up stable patterns without canceling themselves out entirely. Incredible.
So far, we've been talking mostly about the electron's spatial behavior, where it is, how its wave shapes up in 3D space, the nodes.
Right, the orbital shapes and energy levels.
But even early quantum mechanics, successful as it was with NL and ML, couldn't explain everything. There were some nagging experimental observations.
Like what?
Things like tiny splits called fine structure in the energy levels seen in atomic spectra, or how beams of atoms behaved when you pass them through magnetic fields. The existing theory didn't quite cover it.
And this led to one of the most famous, maybe most baffling experiments in quantum history, the Stern-Gerlach experiment.
That's the one, back in 1922. What Stern and Gerlach did was they fired a beam of silver atoms, neutral atoms, but each has one unpaired outer electron through a specially designed magnetic field.
A non-uniform field, right. That was important.
Crucial, because a non-uniform field exerts a net force on a magnetic dipole. Now, classically, you'd expect these atoms, each acting like a tiny magnet due to the electron, to have random orientations.
So hitting the detector screen, they should just spread out into a continuous band. Or maybe just pass straight through if they weren't magnetic.
Exactly. You'd expect a smear, but that's absolutely not what they saw.
What did they see?
The beam split into 2 distinct separate beams, just 2 spots on the detector.
2. Not a smear, not 1 spot, but exactly 2. That must have been shocking.
It was completely unexpected. It revealed that the electron possesses an intrinsic magnetic moment, and crucially, this moment can only take on 2 specific quantized orientations relative to the magnetic field. Not a continuous range, just 2 possibilities.
And more down, basically.
Essentially, yes. This led Uhlenbeck and Goudsmit to postulate electron spin, an intrinsic angular momentum, as if the electron itself was spinning.
Which gives us the 4th quantum number.
Right, EMS. The spin quantum number, which can only have 2 values, plus 12, which we call spin up, and Angle 212, spin down.
And this completed the picture. Describing an electron now needed 4 quantum numbers. N, L, M, L, and Ms.
Yes, and it's foundational to the Pauli exclusion principle, the rule that says no 2 electrons in an atom can have the same set of all 4 quantum numbers. That principle dictates how electrons fill up the orbitals and essentially builds the entire structure of the periodic table.
Okay, but you said as if it was spinning. The name spin is a bit misleading, isn't it?
It is quite misleading, actually. It's a useful analogy, but if you try to take it literally, as a tiny ball physically rotating,
It breaks down.
badly. For an object as small as an electron to have the measured angular momentum, its surface would have to be moving faster than the speed of light, which, violates relativity. Big problem.
Okay, so definitely not classical spinning.
Definitely not. Plus, the relationship between its spin angular momentum and its magnetic moment, the gyromagnetic ratio, is almost exactly twice what you'd expect from a classical spinning charged sphere. It's anomalous.
So it's not a rotation in space, but something more fundamental, an intrinsic property of the electron.
That's the standard view. It's a purely quantum mechanical property, intrinsic like charge or mass.
So how does our idea of frequency cancellation apply here if it's not about spatial waves interfering? We need to generalize the idea, right?
We do need to generalize. Think about the electron's state, its wave function. In a more complete picture, it's not just a spatial function, it's what's called a spinor. You can sort of visualize it as having 2 internal slots or components.
One for spin up, one for spin down.
Exactly. One component corresponds to the spin-up possibility and the other to the spin-down possibility. It's like the electron inherently carries the potential for both states within its mathematical description.
Okay. And these 2 states, spin up and spin down.
They are orthogonal.
Orthogonal, like perpendicular lines in geometry.
That's the mathematical analogy, yes. It means they are maximally distinct, mutually exclusive. If a state is purely spin-up, its spin-down component is 0, and vice versa. They have no overlap in this abstract internal state space.
Ah, okay. So where's the cancellation?
The cancellation here happens upon measurement. When you measure the electron's spin along a certain axis, say the z-axis, the system is forced into one of these basis states, either purely spin up or purely spin down.
It collapses.
It effectively collapses into one state. The cancellation is the zeroing out of the orthogonal component. If you measure spin up, the spin down part of the spinor just vanishes. It's a manifestation of mutual exclusion in this abstract internal state space rather than spatial destructive interference.
That makes sense. It's cancellation in a different kind of space, an internal state space, not physical waves overlapping.
Exactly. Now, there are some, let's say, less mainstream ideas that try to picture spin more literally, maybe as a real rotation of a sort of spread out blob of charge within the quantum field itself.
But that's not the standard textbook picture.
No, the standard picture treats it as this fundamental, intrinsic, two-valued quantum property.
And regardless of how we picture it, this abstract property is incredibly important, right?
Absolutely crucial. Electron spin is essential for understanding magnetism, ferromagnetism in particular. It underpins the Pauli principle, structuring the periodic table. Modern technologies like MRI rely directly on manipulating nuclear spin, which is related. And of course, spin is the basis for qubits in many quantum computing approaches.
So even this non-spatial cancellation or orthogonality has huge real-world consequences. This whole frequency cancellation model, thinking about stability and structure arising from interference, it's really powerful. And it feels quite elegant, especially when you realize it has echoes in things we engineer ourselves.
It does, doesn't it?
Yeah.
It shows a kind of universal principle at play with waves. Think about noise-canceling headphones.
Right. I use those all the time. How do they work again?
Well, they have microphones that listen to the ambient noise around you. Then the circuitry inside instantly generates an anti-noise sound wave that's exactly 180 degrees out of phase with the incoming noise.
So crest meets trough again?
Precisely. When the original noise and the generated anti-noise combine at your eardrum, they interfere destructively. They cancel each other out, creating silence, or at least significant quiet.
That's literally frequency cancellation in action.
It is. Or think about advanced wireless communications, like in our phones. Interference between different signals is a massive problem.
Yeah, dropped calls or slow data.
Right. Engineers design sophisticated interference cancellation systems, or ICS. These systems can identify an unwanted interfering signal, estimate its properties, create an inverted copy of it, again 180 degrees out of phase, and subtract it from the signal they actually want to receive.
Cleaning up the signal by canceling the interference.
Exactly. And the way an electron self-annihilates if it tries to exist in a disallowed energy state, that's a direct quantum analogy. It's nature's own interference cancellation system, ensuring only stable patterns persist. It really highlights the universality of wave mechanics.
Okay, so let's sort of recap where this model works best and where it becomes more abstract. Where is the frequency cancellation analogy most direct?
It's strongest, most literal when we're talking about the spatial aspects. The quantization of energy levels in an atom. That's directly due to the requirement for constructive interference of the electron wave wrapping around the nucleus.
Integer wavelengths fitting in.
Right. And the formation of those nodal surfaces in 3D atomic orbitals. Those are literally the geometric locations where the electron's standing wave undergoes perfect destructive interference, where it equals zero.
You can basically see the cancellation pattern in the orbital shapes.
You can. And it also applies beautifully to how atomic orbitals combine to form bonding and antibonding molecular orbitals in chemistry. Bonding orbitals result from constructive interference between atoms, antibonding from destructive interference. The analogy is very direct there.
Okay, so energy levels, orbital shapes, bonding very direct. Where does it become more of an abstraction?
It requires more abstraction when we get to electron spin.
Because it's not spatial.
Because it's not spatial. The concept of cancellation there has to be generalized to that mathematical idea of orthogonality in an internal non-spatial state space. It's about mutually exclusive states, AO, rather than waves physically interfering in space. The core idea of exclusion or cancellation persists, but the mechanism shifts from physical interference to mathematical orthogonality.
So the analogy holds, but we have to stretch its meaning a bit for spin.
Now, this model, grounded in how the wave function evolves according to the Schrödinger equation, it does a brilliant job explaining why the quantum world is discrete, why we have specific energy levels, specific orbital shapes, specific spin states.
It defines the allowed possibilities, the stable structures.
Exactly. It gives us the menu of allowed states for any quantum system, determined by these rules of constructive and destructive interference, or orthogonality.
But And this feels like a really important, but there's something it doesn't explain, right?
That's right. This is the crucial limitation. The model, based on the deterministic Schrödinger equation, perfectly explains why only certain states are possible. It explains the menu.
Okay.
However, it does not explain what happens when we actually measure a system that could be in multiple allowed states at once, a superposition.
Like an electron that's potentially both spin up and spin down before we measure it.
Precisely. Why is it that when we measure it, we always get only one definite outcome? Either spin up or spin down. Never something in between, never both. How does the system choose which allowed state to manifest upon observation?
Ah, the collapse of the wave function.
Often call that yes. This is the infamous quantum measurement problem. It's arguably the deepest, most debated mystery in the foundations of quantum mechanics.
So, frequency cancellation explains the options on the menu, but not how or why a specific dish gets served when we look.
That's a perfect way to put it. And this is where the different interpretations of quantum mechanics come. In Copenhagen, many worlds, pilot wave theories, and others. They aren't generally disagreeing about the menu itself, the allowed states predicted by Schrödinger's equation and interference. They're offering different stories about what happens during the act of ordering the measurement itself.
So just to be clear, the interference that creates the stable allowed states is a continuous deterministic process described by the math.
Yes.
But the selection of one of those states when we perform a measurement still appears, at least on the surface, to be a probabilistic, maybe even discontinuous event.
That's the crux of the problem. That apparent jump from a state of potentiality, superposition, to a state of actuality, a single measurement outcome, is the central enigma that the frequency cancellation model by itself doesn't resolve. It's still hotly debated today. So pulling it all together, what's the big takeaway from our deep dive today?
I think for me, it's this profound idea. The universe we see, the stability of matter, the structure of atoms, the rules of chemistry, it's all fundamentally rooted in the wave nature of particles.
And specifically, in the way those waves interfere. The discrete, ordered nature of reality at the smallest scales isn't arbitrary. It's a direct, necessary consequence of this principle of frequency cancellation or wave interference.
Yeah, only certain patterns are allowed to exist without destroying themselves. This model, this analogy, it really helps bridge that gap between the abstract mathematics of quantum mechanics and a more physical intuition. It lets you kind of visualize why things are the way they are.
It reveals that the stability of atoms, the incredible diversity of the elements in the periodic table, maybe even the nature of fundamental forces, they all trace back to these intricate patterns of interfering waves.
It's like you said earlier.
Ultimately, the universe is a symphony. And the phenomena we observe, the particles, the structures, the interactions, are simply the notes that, according to the fundamental laws of wave mechanics, are allowed to sound, the stable harmonics.
Which leaves us with a truly provocative thought to end on. If reality is built from the notes that don't cancel out, what other silent notes might be out there? What possibilities are perpetually canceled, existing only as mathematical ghosts, forever defining the boundaries of the reality we can experience?
What reality filters itself out?
Something to ponder. Thanks for joining us on this deep dive.